record on this. Okay, so started recording. So last time we talked about why we do have abnormal pressure. One of the main reasons is that kind of very quick overview that you will have basically formations. Or let's say this is surface, right? And let's say this is a formation at 7,000 feet. And then all these rocks are kind of, these are your rocks, right? All the way go down to the formation that we are interested in. And let's assume that this formation that we are talking about is abnormally pressured. Okay. What is the reason for that? What could be the reason? There are many reasons we discussed last time, but one of the main reasons is that when you have a normal pressure gradient, which means that the pore pressure gradient is constant depending on the location. It could be somewhere between 0.433 psi per feet to 0.5 psi per feet. So depending on which area you are, most likely it's close to this number, 0.433. So in the normal pressure gradient zone, all these pores that you see are hydraulically connected. So underground, there is no pore space that doesn't have anything in it. That's the first concept you need to know. There is either water, gas, or something in it. If there is a pore, there is something in it. Okay. And usually it's water, salt water, something like that in those porous spaces. And when we talk about normal pore pressure gradient, we mean that all these pores are connected together hydraulically, right? So when they are hydraulically connected together, that means that it's like a pool, right? If you have a pool, all these points are connected hydraulically together and you have a constant pressure gradient, right? So that is the case when you have a normal pressure gradient. Now, if you have an abnormal pressure gradient, then one of the reasons could be that you have a shale formation here that have very, very small permeability, right, and porosity. So it blocks the communication between the formation and other rocks. And the reason that the pressure here will be higher than other places is that you have all these overburden pressure, which is the weight of all the rocks on the top of the formation that we are talking about, applying force to this system here, right? And then the water or whatever oil or gas which is present in this formation cannot escape anywhere else, right? So it gets compressed, so you have an abnormal pressure. Now in drilling, this is very, very important because you do the casing design based on this. You need to design your mud weight based on the abnormal formation pressure, right? So you would need to understand what is the pore pressure, right? And for our purpose here, we do design both the mud weight, right, and casing design. That's one of the goals that we are talking about it here, right? Any questions here? All right. So, well, before drilling, there are methods. After drilling, before drilling, and during the drilling, there are a couple of methods that you can determine the abnormal pressure. And before the drilling, you can use the nearby wells. If there are wells drilled in the area, you can use the information from those wells or any geologic information about the same field that you are drilling through, information about type of formation that are there, what is the normal pressure gradient in that area. All this information can help you to decide that. Seismic data is another part. Anybody knows what is seismic?
Waves.
It's waves, right? Acoustic waves that basically they send to the through the surface, right? So there are devices that creates a wave, acoustic wave into the underground, and then there is a receiver that receives that back, right? Now these basically devices that send the acoustic wave, they go to different depths, and based on the different depths that they send these seismic waves, and depending on how much they receive it back, they can correlate those wave information to the type of formations that are available underground. So there are kind of a whole area, right? The geophysics course that is not currently offered in geology department was basically talking about this, all these different methods of seismic. So that also could help in determining the formation pressure. So we're not going into the details of that. But one of the things that basically we use is the well logs. Well logs could be used to determine the formation pressure. There are different types of well logs. For example, one way of correlating the pore pressure to these well logs is that, for example, if you use a density log, density should increase with depth, right? Because of more compaction, right? More weight of the rock on the formations as you go deeper, right? But if for any reason one of the formation that you are drilling through at higher depths have a lower density than the formation at shallower depths, then that's a sign of abnormal pressure, right? Because there is a fluid, right, inside that formation that is putting too much pressure on the rock, and that's why the density is lower, right? The density of the fluid is usually much lower than the rock. Usually rocks are around 2.65 gram per cubic centimeter. This is, for example, for sandstone. Fluids have low density. Usually water is 1, right, gram per cc. Gases are very low dense fluid, right? So if you have more fluid, your system will have lower density, right? And it could be attributed to the porosity, as we discussed last time as well. The porosity also reduces with depths, right? Because again, more compaction. So the higher the density, it would take more time for those acoustic waves to travel. The higher the density, the faster those waves will travel through the rock. And then on the other hand, you will have less travel time. Travel time, this is about the sonic logs. Sonic log sends an acoustic wave into the formation and measures the velocity of those waves, okay? And velocity of the wave is equal to 1 over travel time. This is not actually time. This is time. They call it travel time, but it's time per unit length. So it's basically the reverse of velocity, okay? The unit usually they use for these logs are microsecond per feet. This is travel time. So it means that that wave would travel, if it's, let's say, 5 microseconds per feet, that means it travels 1 feet in 5 microseconds, right? Anyway, so if you have more dense formation, then that velocity increases, and that means that this travel time drops, right? So you can see that as depth increases, based on this picture, average interval velocity also increases. Normal compaction, right? Now, if you go to a formation that doesn't have a normal compaction, it means that it's abnormally pressured formation, then this trend would change, which we will see it later on. So this is an example of those, velocities. If you use sonic log, for example, in air, the velocity is 1100, in water 4600, in low density high porosity rock 6000, and dense dolomite, which have very low porosity, it's much higher, right? So that means that the travel time drops as well, because this increased travel time drops, right? So they are kind of the other way around. So you can see in this picture as well, this is the transit time. Transit time drops, velocity increases, right? This is the transit time. So normally your transit time should drop. And if you see that at some locations, your transit time starts to increase, this area is abnormally pressured. That's a sign of abnormal formation pressure. Okay, this is normal compaction or normal pressure gradient area. interval. This is abnormal pressure interval. Now, usually we extend this normal compaction trend and we call it normal compaction trend line, NCT. Okay, we will use this in our calculation. Kind of we discussed it last time, a little bit, right? But this is the actual. This solid line here, this dashed line here is the extrapolation of that line. Okay, now still we haven't talked about the equations. Okay, so different methods while drilling. You can use penetration rate. Many methods have been developed. The main one that we talk about is called D exponent. We will talk about it today, and modified D exponent. The rest we don't talk about them. Cutting characteristics, what type of cuttings you have at the surface. There is a whole area of research and science about those cuttings that you get on the surface and analyze them. There are many companies, actually, startup companies created based on analyzing the cuttings that you get from the wellbore and relate them to the formation properties. So that's an area. We don't talk about this. We just talk about the penetration rate. Gas cut mud, I don't know, measured while drilling, hole conditions, different things that you can use to calculate the pore pressure and find the abnormally pressured formations. But in this lecture, we just going to talk about the penetration rate and the exponent method. So the exponent method is basically one of the most famous methods. Penetration rate in drilling is a function of many properties. So can you guys give me some of those examples? Any idea why? What parameters would affect the penetration rate? Of penetration rate means that at what speed are you drilling, right? For example, the unit is feet per hour. And what do you think if you are drilling in an area, right, that in a field, what parameters would affect your penetration rate? What would increase your penetration rate? What would decrease that?
Probably like the rock thickness would be a big factor.
The rock thickness. Let's assume that you have same rock thickness, right? Let's say you want to drill 100 feet interval, right? And it's a rock now in two different areas, right? Now, what if you're basically drilling the same interval, what parameters would affect that speed?
Is the mud density?
The mud density, that's one factor. Okay, what else?
Matrix density.
Matrix density. So let's go back. How does mud density increase or reduce your drilling rate? If you have a higher mud density, do you think that you would drill faster or you would drill slower? Slower, right? So the higher the mud density you use, it's going to be a slower drilling. And that's why one of the reasons that people are attracted to underbalanced drilling means that you use basically lower mud density in your drilling is because it has higher speed, right? So lower mud density is one factor. Matrix density, if you have harder rock compared to a soft rock, that would definitely change your penetration rate, right? What else?
The type of bit you use.
The type of bit, right? Definitely. I mean, there are many, three main basically drill bits, and each bit is designed for a specific type of formation, right? And you kind of did some calculations when we did the price per feet calculations of the drilling cost per feet, right? Different drill bits may have different rate of penetration, right? What else?
The tension, maybe?
What's that?
The tension on the bit. How much you're gonna put?
Well, that's not called tension, but it is called weight on bit, right?
Weight and bit, yeah.
Yeah, so weight on bit is also an important factor. So weight on bit means that what is the weight of all these drill string system applying on your bit, right? Now, if you have higher weight on bit, right, you're probably gonna drill faster, right? But also there is another factor that combines with weight on bit. What's that? When you drill, you also rotate, right? You rotate your system, right? So you rotate your drill bit. So basically a combination of weight on bit and speed of rotation of your drill bit is the main factors that basically play an important role in how fast you drill, okay? So weight on bit, size of your bit, the speed of rotation, these are the three main factors. There are many other factors you see in this equation that the parameters are not basically told what they are, but there are multiple. I think if you check the drilling book, there's a chapter about this, and I think around 9 to 10 factors are mentioned that would affect your drilling, right? The compaction, the depth at which you are drilling, the porosity of your formation, all these factors that you guys also mentioned, they also play a role, right? But they came up with this equation for your drilling, and K is basically a constant, and is the ROP, rate of penetration. N is the RPM, which is how fast you're rotating your drill string system. W is how much weight is on your bit. dB is the diameter of your bit, and D is called D exponent. So if you calculate D exponent, if you solve that equation, the D exponent, this equation becomes this, and this is one of the factors that decides about you can use it as a indicator of your pore pressure. So in this equation, R should be in feet per hour, N should be in RPM, weight on beat should be in pound force, or pound mass. Basically, D is the exponent, and diameter of the bit is basically the inches, right? Now, in normal drilling, you will have, let me, before talking about the exponent, let me see, where is it? Not here. Okay, so let me see. In normal drilling, you have basically your D exponent changing linearly in normally pressure formation, and if you have an abnormal pressure formation, then it will have the same trend as it will have a different trend from normally pressure formation. If you go back, I guess, a couple of slides here, the exponent, you see it here. So this is normally pressure formation, and if you plot the exponent versus depths, right, you will see that it has a normal trend, right, up to some specific point, and once you enter the abnormally pressure formation, the trend changes, right? Now, comparing at the same depths, comparing a normally pressured formation with the current abnormal gives you a tool to calculate what would be the abnormal pressure, right? Now, there are many correlations based on that, which we only talk about one of the correlations here. But this D exponent also have been modified based on the density of the fluid, okay? So density of normally pressure gradient formation versus effective mud density in use. They modified this exponent because, as you guys also said, the mud density would affect your drilling rate, right? So they wanted somehow the mud density to be in the equation of ROP, okay? Now, in this equation, you don't see K because if you solve this for two basically cases, comparing two different cases, that K parameter would be eliminated, okay? Now, this can be modified, of course, right? To this, we call it DC exponent. This is D, this is DC. This is more reliable compared to D exponent. So if you have DC here in this equation, Okay. Anyway, we don't use also this in your project, this method. This is also another basically method to do that. But what we use is basically the well logs. And well logs, there are many well logs: resistivity log, conductivity log, sonic density, right? Each of them could have different trends. And the main equation that we use is called the Eaton's method. And Eaton's method is described here with this equation. This is, I'm going to describe what this equation means. So first look at the left side, this picture here. This is depth, right? And this is basically any parameter that is an indicator of your pore pressure. Now, those parameters could be what? Could be resistivity log, could be conductivity, could be sonic log, delta T, travel time, right? It could be the density from the well log that you are getting, right? Resistivity is shown with R, right? Conductivity is shown with C. So any of these type of measurements, or even the exponent, okay, you can use it in this equation. So this parameter K that you see here could be any of those parameters. They have all same equation, okay? But one parameter there is different, but we'll talk about it. So anyway, this is pore pressure, right? PP here, you see pore pressure in pound per gallon. OB is called overburden stress. And usually this is 1 psi per feet, right? And anybody knows what is one? Now, the units that you see in this equation are in pound per gallon, right? How can I convert 1 psi per feet to pound per gallon? So I want to convert psi per feet, 1 psi per feet, which is the normal overburden stress, right, to pound per gallon. How can I do that? Come on, guys. You know that. It's very easy.
Is it like 51 maybe?
What's that?
Is it 51 something like that? No.
Yeah, how did you get that number?
Like a 51 psi, 51 psi per feet.
No, this is 1 psi per feet. I want to convert it to pound per gallon. So how do I convert this pressure gradient to an equivalent density? Any idea?
Is it like 0.59 something like that?
So the pressure, yeah. So the pressure for pressure was equal to 0.052 density depth, right? And pressure over depth is called psi per feet, or gradient. That's what it is, right? Is equal to 0.052 multiplied by density. So all you need to do is density is equal to 1 over 502 multiplied by your pressure gradient. In this case, it's 1. So it's 1 over 0.052. Okay, so it's around kind of close to 20, I guess, right? Pound per gallon. So that's your overburden stress here in this equation. Make sense? All right, so that's, and then you have the normal pore pressure gradient. So depending on where you are, pore pressure gradient is 0.433 or 0.465 psi per feet. You can convert that into pound per gallon, use it in this equation, right? And what else? This is the normal, right? And then you have K. So K, there are K parameter, which could be resistivity again, conductivity, transit time, density, DC exponent, any of those parameters. There is a normal one, which is the extrapolation of the normal area, right? At the same depths. And then there is one that is actually came from your well log, right? The real value. So if you divide KO by Kn to the power of m, which is called Eaton's exponent, then you can calculate the pore pressure. Now, for transit time, you should use m equal to -3. For resistivity, you use 1.2. For DC exponent, you use 1.2. Okay. Now, if you go to your project, you'll see that the transit time and resistivity are given to you, the well logs, right? At any depths, you would need to digitize. It's a graph. Let me see if I can open that part. All right, this is your project, right? And let me see if rotate here. All right, so these are two well logs that is given to you, right? So I'm going to do an example maybe here on this well log. You see that the top part is, this is resistivity in milliohms, right? So this is ohms, means that it's resistivity, right? And this is microsecond per feet. So this is transit time. So this is sonic log here. And this one is resistivity log, right? This pen is playing right now. Let's see. All right, so resistivity and sonic log, right? Resistivity. Okay. All right. So now you guys can identify where the normal compaction trend is, right? So this line here, which is linear, this part is the normal compaction trend. And then this part, which is dashed, this is the extrapolation of that part, right? So you can see it here as well. So how these measurements are done, you guys know about the well logs, right? So this is a device they send into the wellbore. It send the signal into the formations as it goes down, receives them back, and this is the results basically, right? So it starts from 5,000 feet here all the way to 15,000 feet. Okay, and what else you would need to do here? So this is your compaction. So let's say you want to calculate using the resistivity, right? At 11,000 feet. So what you need to do is to calculate all these pressures at all the depths. Okay, especially you want to start from the abnormal pressure formation, because I believe the normal pressure gradient is given to you. If I should, it's not given, I guess. No, not there, but you can assume it to be 0.433 psi per feet. It might be here, I'm not sure, but if it's not there, just assume 0.433 psi per feet for your normal pressure gradient, right? And then at any point, let's calculate it at 11,000 feet. Let's say it's here, right? This is 11,000 feet depth. I'm going to use the resistivity. So there is a normal point, and then there is a abnormal point, right? So now what is the equation? Let me go back there. The pore pressure is overburden pressure minus pore pressure is equal to overburden pressure minus overburden minus, again, normal pore pressure. And then this is multiplied by KO over KN to the power of M, right? So this is the equation I need to use, right? And for resistivity, I need to use an exponent of 1.2. So this M for me is 1.2 1.2. Sorry, this pen is not working properly today. And KO is actually resistivity O, right? And that should be RO, and this should be RN, right? That's what I need to do. This is 1.2 here. This is my equation, right? Now, at this point, at 11,000 feet, and overburden pressure, I believe, is also should be given to you. If not, just assume 1 psi per feet. So let's assume that it's pump psi per feet. So pore pressure is equal to overburden pressure, which is 1 psi per feet. And if I need to convert it to pound per gallon, I need to divide it by 0.052 based on the equation that we discussed here, right? You just need to divide whatever psi per feet that you have by 0.052, right? So I divide that by 0.052 minus overburden pressure again, 0.051 over 0.052. Again, this is psi per feet, right? That's what we assumed. Minus the normal pore pressure gradient. Now, the normal, again, this is another assumption based on the area that you make, right? If I think I mentioned which area this could be, so you can refer to that in more details, but let's assume here 0.433 psi per feet converted to pound per gallon. And then multiply this by the resistivities, right? So what is RO here? What number should I read for RO?
Resistivity of the abnormal.
Right, and that is around 1,000, right? So let's assume 1,000. And then let's assume 1,000 here. And then you have your normal pressure gradient at the same depths, that is 400, right? 400 milliohm to the power of 1.2. And that's it. Once you calculate this is give you the equivalent pore pressure in pound per gallon. And you would need to convert this pore pressure to, so let me see, let me calculate it here. That is 1 divided by 0.052, that is 19.23 minus 0.433 divided by 0.052, that is 10.9, so that should be around, so that is 10.9, and 19.1 minus 10 point, and then 10.9 multiplied by 1,000 divided by 400 to the power of 1.2, right? And that is going to be 32. That seems to be negative. Let me check, double check here. I think I did a wrong calculation somewhere. 5.2 minus 1 divided by 5.2 minus 3.3 divided by 0.0. 5.2 multiplied by 1000 divided by 400 to the power of 1. No, that becomes negative. I believe something is not correct here, and that should be probably this power. I think this power should be minus 1.2. Yeah. So this power here for resistivity is minus 1.2, not 1.2. So this needs to be fixed. I'll check the book as well to make sure. But this became 15. The result of this became 15.6 pound per gallon. Okay, and then you can convert this again to PSI per feet, of course, right? So multiply that number by 0.052 gives you the PSI per feet, which becomes 0.81 PSI per feet. And then at 11,000 feet, so that means that you multiply that number by 11,000 to give you the pressure. So that is 8,000. So this number multiplied by 11,000 feet is equal to 8,922 PSI. So this is your formation pressure. Make sense? And then you can calculate also what would be the normal pressure. So it's simple if you assume that it's 0.433 PSI per feet multiplied by 11,000 feet, that is 4,763 PSI. This is the normal pressure, if it was normal, right? But it's not normal. It's 8,922 PSI. Okay, so you need to do that at all the depths that you see here for your project. You need to digitize this well log, right? And once you digitize it, you calculate it for all the pressures that are in this. You can either use this resistivity or you can use your transit time. Either one is okay. Okay, you don't need to do both, just do one of them. Okay, results should be similar, very close to each other. Okay, and once you calculate this, then you have your pore pressure, right, which is this line here. So you will have this line with depths. And then you can calculate, you can add 0.5 pound per gallon to that curve, right? Which you get your trip margin. So you established this line. Next thing you need to do is the fracture gradient, which I will discuss it next time. It's just one equation again. Again, Eaton's method, very similar to this one. But we'll use that, equation. Then you can establish the other line too. And once you did that, you can start basically designing the depths set of your casings, and then start actually designing your casing. Okay. Any questions? No question?
Oh, we're good.
All right, cool. So the calculations here is not for pressure very complex, right? It's just a single equation with different bell logs. So you can just, do it, not very complicated, I believe. What did I do? All right. So if you have any questions, let me know. And please try to work on that homework, the extra point, which helps you. If you can do that homework, definitely for the exam, you will be, that homework is definitely harder than the problem that you will have in the exam. So if you can do that homework, then in the exam, you can simply do the calculations for casing design. All right, so I'm gonna stop recording and